Hi everyone, I'm Pratyush and I'm here to talk about our system, ZEXE, which enables decentralized private computation. This is joint work with my excellent co-authors Sean, Alessandro, Matt, Ian, and Howard. Alright, let's get started. So today, if users want to compute on general distributed ledgers, they have a variety of options such as Ethereum, Tezos, EOS, and many more. And the common thread amongst all of these systems is that they all work by re-execution, which means that to verify a transaction, every node has to re-execute every computation inside that transaction. Now, this has implications for both the scalability and privacy of the system. From a scalability perspective, the problem is that if your network consists of nodes which have different computing power, then transaction verification is bottlenecked by the weakest node. And this is a problem even if you have the best underlying consensus mechanism in the world. You still have to wait for the weakest node to verify the transaction. From a privacy perspective, the problem is that the transaction reveals information about the executed program, the input data, as well as who invoked that program. And this information is stored on the ledger permanently, so anybody can retrieve it even 100 years down the line. Okay, so to solve this problem, we propose ZEXE, which stands for Zero Knowledge Execution. This is a system for allowing users to conduct computations offline and then publish transactions attesting to the correctness of these computations to the ledger. Right. From a privacy perspective, what ZEXE guarantees is that the transaction reveals no information about the offline computation, which means that which program was executed, what data was provided as input to the program, and who invoked that program. All of that information is completely hidden. Next, from a scalability perspective, what we guarantee is that the transaction can be validated in time that is independent of the underlying computation. Concretely, for our system, this means that transactions are of size less than a kilobyte and can be verified in less than 50 milliseconds, which is an excellent guarantee. Now, to achieve these strong privacy and scalability guarantees, we do not sacrifice functionality. Rather, our system allows users to define and execute arbitrary computations while still allowing these user-defined computations to interact in a secure manner. Finally, we leverage these properties to construct interesting private analogs of various applications that users are interested in, such as private user-defined assets, private stablecoins, and private decentralized exchanges that allow users to trade both of these. Okay, so let's dive in and see how ZEXE actually works under the hood. Okay, our starting point will be the Zero Cash protocol because it serves as the basis for our construction, but also it demonstrates how to achieve strong privacy guarantees for a simpler case of private currency transactions. Okay, so in Zero Cash, each transaction consumes some old coins and creates some new ones in a manner that completely hides the sender, receiver, and value of every coin in the transaction. In more detail, a Zero Cash transaction consists of some serial numbers corresponding to the consumed coins and some commitments corresponding to the new coins. And the guarantee is that there's no way to link a transaction that creates a coin to the transaction that spends it, i.e., the anonymity set of each transaction is a set of all created coins. Okay, this is a very strong privacy guarantee. Let's see how Zero Cash actually achieves it. So as I said, in Zero Cash, a transaction consists of serial numbers corresponding to the old coins and some commitments corresponding to the new coins. To check a transaction, we have to do two things. First, we have to verify that the serial numbers in the transaction don't appear in any past transaction. So this is a double spending check. Next, we also have to validate a zero-knowledge proof that asserts some properties about the old and new coins. Namely, it asserts that all of the coins that we're spending actually exist via a proof of membership in a commitment Merkle tree. Next, it asserts that the serial numbers for these spent coins are actually derived correctly, which ensures the soundness of our double spending check. After that, it checks that the new coin commitments are constructed correctly, so that they actually contain values and not just some arbitrary garbage. And finally, and perhaps most important, the zero-knowledge proof asserts that value is conserved, which means that the sum of the input values is equal to sum of the output values. Okay, this is a very high-level sketch of Zero Cash. The key thing for us to take away is that this is actually checking a specific computation over data of a specific form. In our case, the data is just integer values, and the computation that we're checking is the value conservation predicate, that value is conserved going in and out of the transaction. Okay, So from this viewpoint, let's try and see how we can extend to achieving arbitrary computation over arbitrary data. Okay, so a natural idea is to look at how Bitcoin achieves this. What Bitcoin does is every coin in Bitcoin is associated with a particular Bitcoin script. And to spend a coin, you have to ensure that the script for that coin is satisfied. So to construct a private analog, we can proceed similarly. So now instead of coins, we consider arbitrary data records, which contain not values, but arbitrary data payloads, and have an associated predicate or script, P. Right? And what the transaction proof will now guarantee is that the predicate associated with every coin that is, or every record, sorry, that's being spent is satisfied. So in this example, the transaction will assert that P1 is satisfied. Now, in terms of implementation, this would look like the transaction proof, just asserting that for every input record, the predicate for that input record is satisfied. Okay, so this is a simple generalization. Let's see if it actually achieves the properties that we want. Okay, from privacy perspective, it works because both data privacy and function privacy are guaranteed by the hiding property of the commitment and the zero knowledge property of the proof. So this is nice. But what about our strong programmability goals? Can we achieve them here? So let's try to see if this is the case by trying to recover a simple example of private transactions. Okay, so in private transactions, the payload of each record is just the value, and the predicate is, as before, the value conservation predicate. So this predicate will look at the input coins, input records, check if they're actually meant to represent currency, do the same for the output records, sum up the values, and check that the value is conserved. Now, what our system so far will guarantee is that if the transaction proof is valid, then if there's a single currency record that's provided as input, the conservation predicate is satisfied, right? So whenever there's a single input currency record, the transaction proof will enforce that the conservation predicate is satisfied. Okay, let's see if this actually works by considering some transaction flows. So first, let's consider an honest transaction. So here, there's some user who has a record R1, and they want to spend it and create a record R2. So they create a transaction, and the transaction proof will assert that the value conservation predicate is satisfied. Okay, and then similarly downstream, another user can spend R2 with the same mechanism. Okay, so clearly, honest user workflows are preserved. What about a malicious user? What can they do? So let's say I'm a malicious user and I have a record which contains garbage, and I want to use that record to create a new record which is actually represents some non-zero value, right? So what the transaction will do, it will say, okay, look, my input is R1, its predicate is a predicate that is always satisfied, right? So then there's no further checks that happen, and so the transaction is completely valid. So what we've managed to do is create money from thin air. Indeed, if a later transaction tries to spend R2, what that user will see is that R2 is indistinguishable from the honest case. There's no way to trace the fact that R2 was created in a dishonest manner. So what we've now achieved is a complete break of the integrity property of the currency. We've allowed undetected inflation to enter the currency, which is a problem. Okay. The reason that this problem crops up is that there are two events in a record's life, birth and death. However, our system only enforces constraints on the record's death. There is no constraint on the record being born. So to remedy this, we propose the record's nanokernel. In this programming model, now each record contains not only one predicate, but two predicates, a birth predicate and a death predicate, and the data payload as before. The transaction proof now asserts that for every record that is consumed, so every input record, the corresponding death predicate is satisfied, while for every record that is created, so every new record, the corresponding birth predicate is satisfied. Okay. So this means that at every step of a record's life, from creation to consumption, there is some constraint being enforced. From an implementation perspective, this will just look very simple. For every input, you check that its death predicate is satisfied. For every output, you check the birth predicate is satisfied. The rest of the transaction proof is unchanged. All right, let's see if we can recover our example of private payments in this new model of computation. So we have our value conservation predicate as before. What it does now is that it checks that the sums of the values across the input and output currency records are conserved. So let's see how this plays out in both the honest execution and a malicious execution. So in the honest execution, you have a user who's trying to spend a currency record R1 and create a new currency record R2 of, let's say, the same value. Let's say R1's death predicate always accepts. And in this case, what will happen is that R2's birth predicate will be executed. And this is a value conservation predicate. It will check that the sum of the values across the input, which is just V1 in this case, is equal to sum of the values in the output, which is V2. And yeah, in this case, if it's an honest execution, these will be equal. And so the predicate will accept as required. Okay, so the honest execution works out as expected. Let's see what happens in the malicious execution. Recall that in this execution, we have a malicious user who's trying to take a garbage input record and use it to create a valid currency record, which has non-zero value. So let's see what happens. So again, the death predicate accepts. But what will happen now is that R2's birth predicate will execute. And this is the value conservation predicate. It will look at the input value and it'll see that it's actually 0, but the output value is non-zero. And so it'll reject, which means the transaction as a whole will be rejected, which is exactly what we wanted. Okay, so in summary, it seems that this new model of computation achieves all of our goals. Data privacy and function privacy are guaranteed as before by the commitment and zero knowledge proof. But now as secure, we can achieve our programming goals because the birth and death predicates constrain every aspect of the life cycle of a record. So in the paper, we show how we can use this now more powerful programming model to construct some useful applications like private user-defined assets, stablecoins, and decentralized exchanges. See the paper for extensive discussion of these. Okay, so this is great that we have this new theoretical model, but how do we actually implement it, right? In more detail, how do we enable the transaction proof to check that the birth and death predicates are all satisfied? So there are two approaches to this. The first is a very standard approach, and that is to use universal circuits. So what happens in this approach is that the transaction proof will interpret every predicate as a circuit, and it will execute the circuit and check that it is satisfied. Now, this universal circuit approach in the context of snarks has been optimized across a wide range of works. However, despite these optimizations, it's still the case that universal circuits are asymptotically and concretely inefficient. So the performance overhead is roughly 20x. Okay. So because of this, in ZEXE, we take an alternate approach, and that is to use proof recursion. The idea here is that the transaction proof, instead of directly verifying the predicate circuit, it will instead verify a proof that attests to the satisfaction of this predicate circuit. Right? And the nice property of this is that recursion is concretely efficient if we can construct small circuits that verify these snark proofs. Now, the problem is that constructing these efficient snark verification circuits requires special pairing-friendly elliptic curves. Okay. So to resolve this problem, what we do in ZEXE is construct special chains of elliptic curves which are amenable to recursion. In more detail, we first demonstrate a new method for sampling recursion-friendly BLS12 pairing-friendly curves. And then we construct a new curve CP6 via the Cox-Pinch method, which allows us to verify predicate proofs that are created over BLS12 377. Next, we also construct special Edwards curves that allow us to efficiently implement Pearson hashes and commitments over both the BLS12 and CP6 curves. All of these curves are implemented in our Rust library, which is available at libzexe.org. Now, these efficient implementations allow us to achieve the excellent transaction size and verification time numbers that I reported earlier. Okay, so to conclude, in this talk I presented ZEXE. We saw how we can use birth predicates and death predicates to model computation over these data records. In the paper, we show how to realize this records random kernel via a cryptographic primitive called Decentralized Private Computation. And finally, we also have a lot more details about our implementation, including this details about elliptic curves, but also efficient circuit design and how to best recursively compose these proofs. Thank you.